Hi, everybody. Welcome to ElasticON AI. It's exciting to have ElasticON again in San Francisco. Our first conference was in a pier about a few blocks down the road. So it's really exciting to be back here and doing these ElasticON events. We're going to do many of them across the world. And this time, we're going to focus on AI. So let's get started. So I'll start by some reflection. I'm a CTO at Elastic now. I took a vacation as a CEO for 4 years, but I'm now back to actually working as a CTO. And I've been in search for years. One of the first users and committers in Apache Lucene, or contributors to Apache Lucene. I worked on an open source project called Compass that was built on top of Apache Lucene, and afterwards Elasticsearch. And I've saw the growth in search and the capabilities that we developed over the years. And one of the proudest things that I have that we've been part of is this evolution of search as a technology, especially in the open source space, beginning with Apache Lucene and obviously with Elasticsearch, that has been there for more than 10 years now. And I remember still that when we were trying to do search, then you had requirements around search. For example, you want to be able to filter all the products between a certain price range to be able to go and find them on a search bar. And the way that you would do it with, for example, Lucene, was to pad the text with zeros, because it only did text search. So we had to go and figure out how do we take numbers and index them in a new data structure so we'll be able to do efficient filtering when you do search. Afterwards, there was a need to do faceting, like really fast aggregation based on the search that you're doing, sort of analytics, if you will. And that was pretty badly implemented in the early days. Like we had to uninvert the inverted index, load it to memory, and do all the computation there. And then over time, we built a whole new columnar store into Apache Lucene. So Apache Lucene has a columnar store called dog values to be able to go and do this aggregation in a really fast and efficient way. This thing called iPhones came out, and suddenly GeoSearch became all the rage, and people wanted to go and do search together with and constrain the searches that they do for restaurants or other things on their phone. So we had to go and figure out how to do GeoSearch, and in the beginning, obviously, it was pretty silly distance-based calculation in memory, and I admit that I kind of like read a white paper and implemented it on a train ride or something like that. But afterwards, we went and implemented a whole new data structure into Apache Lucene called BKD trees that probably makes today Apache Lucene and Elasticsearch one of the most popular, if not the most popular, geo database in the world, which is extremely exciting and extremely efficient. So there has been tons of investments over the years in search, and obviously a big part of it is around vector search now, which we're going to talk about in a few seconds. And search has changed, and it's exciting to see. One of our deeper beliefs is that search unleashes data. Like you have data that comes in many different shapes and forms, and you need to be able to go and explore it. And search is the most human and effective way to interact with data. You put a search box in front of someone, they know how to go and interact with it. And AI really empowers that experience. And a big part for us is doing that together with a community of users. Billions of downloads, community members, developing all of it together and building this search technology moving forward. And obviously, over the past year, an inflection point happened, and AI or Gen AI came along. Now, obviously, this is the slide where you ask an AI to generate a slide. So you have to have it in every talk. I think it's really weird. The last one looks like a Roman dinosaur or something like that, but I guess we're men, so we have to think about the Roman Empire. And Gen AI, I remember like about a year ago or so, everybody were like, I don't know, it happened. It's almost like felt like a day. People were like, search is dead. Gen AI is the thing. It's going to kill search. Elasticsearch is not relevant. Lucene is such an old technology. Nobody uses it. It only does text search, and it's not relevant. And I was like, really interesting, because let's talk a bit about it. And by the way, this slide probably applies to a lot of different things. Like you could put humans there or something like that if you talk to Max or others. So it's really interesting, but we're focusing on search here. And we really want to work and try to understand, what does it mean? Does search has a place? Does it really has a place in a Gen AI world where we have these workflows and large language models? And yes, it seems like search is more important than ever. And it took us time to try to figure out what is that place. And I'd love to take you through some of that journey that we took and what we plan to develop into the future. So first of all, Gen AI is composed of something called the large language model. And one of my favorite terms that has started to emerge in this space is grounding. Like, all of these large language models needs to be grounded. I mean, all of us probably needs to be grounded a bit, but definitely large language models needs to be grounded. What does it mean to be grounded? Well, they can hallucinate. Like, if you don't give them context, if you don't try to shape them towards giving you the right answer, they can really go off the rails, and we've seen some examples of it. And it's really tricky, right? It's like, if you put it in front of your customers, if you put it within your company, this is something that you need to think very deeply about. Like, how does the engagement with a large language model look like, and trying to understand how to shape it and constrain it. It's also not powered by your data. You're building a business that probably has fast-moving data that keeps on changing. Your business generates data, whether it's internal companies' data, whether it's customers' data. That's not powering the Gen AI capabilities. Like, it's an extremely smart capability in large language model, but it's not being powered by your company's data. And how do you think about security and privacy? What is allowed to see? Some roles in the company can see certain types of data, other roles cannot. How do you make sure that people don't have access to the data that they don't need to? And how do you make sure that people that do need that access actually have that access? Because that's a very empowering capability. And this concept kind of like emerged over the last, more than 6 months or so, called Retrieval augmented generation, or RAG. And what does that mean? It means that when you ask a question, or when you engage in hopefully in a very natural language way, you can feed that question to the large language model that you're using. But probably what you want to be able to do is to give it context. For example, we're developing an AI assistant for some of our solutions, which we will show you. And the first thing that we tell the LLM to do is, hey, you're a very helpful and amazing and nice large language model that really wants to help people fix their security problems. Like, you really want to encourage the LLM to do things. So this is context. This is like, how do you shape the LLM to be able to go and do it? But there's the shape of the answer. There's also the content that you want to feed to that answer. And that context is critical to the success and the relevance of the answers that LLM is going to give you. And that comes from your business data, whether it's the customer's data, whether it's your company's internal data, that keeps on changing extremely fast, and you want to be able to give the best context possible. And that context is limited. So when you're trying to feed an LLM a context, it's pretty constrained space. It's like, it depends, it keeps increasing, but it's not infinite. It's a bounded amount of tokens, 4,000 tokens, 20,000 tokens. So really, the ability to provide the most relevant context will make or break your user's experience when it comes to using an LLM. Now, you see here, you can put your business data probably in a relational database. You can put it in a data lake. You can put it in a document database. But all of these systems are missing a very critical capability. Because you're really bounded by the context, the size of the context that you can provide that LLM, the relevancy of the data, of the results that you're going to feed into that context from your data matters so much. You can imagine that if you give that LLM a slightly different context, you're not that helpful AI, and maybe you don't want to please the answers to you that you're giving to your users, that's going to make a big difference to the users that use it. So the relevancy of the data that you fit into that context window matters a lot. And guess what? Search engines are pretty good at providing very relevant results and being able to be a part of that context. And we've taken that set of capabilities, the ability to go and build an inverted index and BM25 and vector search and all of those things that we do so well at Elastic, We package it under something called Ezra, the Elasticsearch Relevance Engine. And we're using it and packaging it to you to be able to go and use it, and you'll see some examples down the road. Now, this is critical. Your business data moves fast. It scales. You know, terabytes, petabytes of data that you want to have. You can't feed an LLM petabytes of data, right? So you need to be able to take this natural language question, translate it to something that you can go back to your business data and get the most relevant results into a very small window. So it has to be the most relevant results to that experience, being able to fit it to that LLM and then get the answer back. And that's like a critical part of the workflow of Gen AI that we're seeing today. And obviously, search plays a huge role in that space. So what is Ezra? Ezra has a set of toolkit of capabilities and APIs to be able to go and develop these Gen AI workflows. It can act as a component in that retrieval augmented systems. It can drive the workflow itself. It has tons of choice of models. You can do text-based search, you can do vector search, hybrid search between them, the ability to filter data to be able to go and build security models. And it's enterprise ready. We've been building search for years now. So the ability to document and field level security, to take that role that the person that searches together with their geolocation, together with which department do they respond to or do they relate to, and being able to take all of that information, filter, to create a window, a boxed window of data that they allow to get, and then drive relevancy out of it. Like, that's a really hard problem to do. And that's what we've been building for many years now. And at the same time that, like, after Gen AI happened, suddenly another thing happened, which is like, all you need is vector search. And vector search became a big thing, and vector search is a critical component of this RAG or Gen AI workflow. And Elasticsearch and Apache Lucene are a great vector database solution. And then next to vector database, you also need the ability to create embeddings. So when you take data and you index it, you generate embeddings to be able to go and search it, those vectors basically. And then when you do the query and you search, you also generate embeddings to be able to do it. So a big part of it is how do you generate the embeddings, what's the model that you're using, this whole workflow as well. And we'll show examples about it in a few minutes. And then there's the whole world around it. How do I take the role of the user, for example, or the department that they belong to, and filter only to the data that they need to be able to see? How do I do aggregations and filtering? How do I take the geolocation of that person or my customer or my user that ends up using it and being able to filter the data only to what they need to see? Because that context window is extremely constrained. And even if it increases in size, and instead of 20,000 tokens, it becomes 100,000 tokens or 150,000 tokens, it's not a step function in size. It will always matter significantly what's the relevancy of that data that you feed, that you put into that context window. So really a great Gen AI workflow is having a great LLM, but also having a great relevancy engine to be able to go and feed that context window. And with that, I'd like to invite Matt. I'll be back, but I'd like to invite Matt to do a demo of some of the things that I've just spoke about, and also show some customer examples, if that's okay. Go for it, Matt.
So I'm going to be doing two demos today that kind of build on each other. And if you think back to the architectural diagram that Shay showed, kind of that top left corner, there's this question about how we pose a natural language question both to Elasticsearch and then also posing that out to the LLM with context from Elasticsearch. And so a lot of the work that we do is around making sure that we can interpret that query in natural language and provide relevant search results back. So the first demo I'm going to do is an approach to semantic search that is actually capable of interpreting those kinds of natural language questions and giving you good search results. And then the second demo is going to take that and kind of pull it all together into a fully functioning retrieval augmented generation workflow like the one that we showed in the full diagram. So we'll move into that now. It'll start off with the BM25 search. So largest city in Illinois. And as you can see, with this is basically a search over a Wikipedia data set, and using BM25 matching, it's basically your kind of typical keyword match, and you can see how it's picked up on the keywords of the query, and those are the things that are matching. If I switch over to the index that's been processed with ELSA, which is basically a pre-processing stage through a transformer model, which changes a bit the documents as they're stored in Elasticsearch, we get a much more semantically relevant result for the query at hand. And I'll show a few different examples of this. So that's one example, banks that went bankrupt. So if we do that, we sort of start to see even more of the kind of the challenges with pure keyword matching, right? It's picking up some of the specific keywords, but it's not really understanding the meaning behind the word. And if you're trying to feed this into an LLM, you really need to understand what that query is. And those queries are going to be starting to come in much more natural language form. So if we compare that again to what ELSA is able to bring back, we get much better results and that have really understood the nuance of what the query is. Maybe the last example that I'll do here is something like funny actor. And again, you get a couple of examples right, but again, you kind of get these, these keyword-based results. And in something like in ELSA, you really get something that works much, much better. So the idea here is to provide semantic search kind of out of the box with Elasticsearch. And what's unique about this is that this is a model commercially available with Elasticsearch. It ships with the software, and you can use it on any content that you already have indexed. So there's really no work for you to do in order to get these kinds of search results and this kind of relevancy out of content that you already have. You don't have to go out and search for the right embedding model if you're doing vector search or anything like that. This is one of the nice attributes of a late interaction model is that they're zero shot. They're meant to work on any kind of text that you throw at them. And as you can imagine, if we're going to ship a model with Elasticsearch, it needs to be something that we're fairly confident will work on whatever kind of content you have in your application. Maybe the very last example I'll give here before moving to the other demo is one in a foreign language, or in German. So this is if we go back to BM25 and type hello world in German, how are we going to do matching a keyword like that? Actually, ELSA today works in English, but we also have support for, which I think we'll talk about a little bit later, we also have support for bringing in third-party models, something like a model that you find on Hugging Face, for example. And so we have another version of this that's running through E5, which is the multilingual semantic search model. And you can see here it actually interprets the language, the German language query, and matches correctly to the English language content. So all of these things are kind of precursors to building a really nice retrieval augmented generation system, which we'll skip to now. So the example here, kind of to set context, this is the idea of building a retrieval system maybe for your internal employees. So what we call workplace search, but basically searching over all the internal data in your intranet and answering questions for employees. And one of those questions might be something like, does Elastic own my side hustle? All right, that's an interesting query in a couple of ways, primarily because the system needs to know how to interpret the term side hustle. What do we match that to? And you can see here at the bottom the search results that came out of our internal system. It's a SharePoint drive, some stuff in Teams. These are the actual search results. Those are the search results that are fed in as the context to the large language model to ultimately generate the answer here. And as you can see, this is the results themselves coming out of Elasticsearch, powered and then passed through to Azure OpenAI service to actually generate kind of the long form answer that comes out here, but grounded in the exact or the proprietary data that is inside of Elasticsearch. So you could probably ask that question directly to a large language model, but it's not clear which intellectual property policy it would be answering from. So we want it to be answering from the one that's specific to our company. Another example here might be maybe one of my favorites, which is what is NASA? And so if you were to ask ChatGPT that, I think we all know what kind of answer we would get. It would be about the Space Administration. But at Elastic, NASA stands for the North America, South America sales region, and that's specific to us. That's very specific to our company, and it comes out of a document giving an overview of our sales organization. And then final example here around, that gets to the point that Shay was just ending on, around how we've worked really hard to build all of the capabilities to enforce things like document level and field level security based on access control and things like that. And in an internal intranet system, some people are going to have access to some documents, others will have access to others. So if you ask a question like, let's see here, how are senior engineers compensated? In this case, because I'm logged in as an engineer, actually it doesn't have information about the entire compensation matrix and all the things that go into that. But if I change my role over to a manager and re-execute the query, we're able to actually find the right kind of content through the search results and then feed that into the LLM and actually provide the answer. So it kind of pulls all of this together, but I think the primary thing to take away from this is in order to build a retrieval augmented generation system like this, you really do need a smart system that can interpret these natural language queries to make sure that the context that we're providing to it is actually going to be the right kind of grounding. So we've spent a lot of our time not just building vector search into Elasticsearch, but also just thinking deeply about what it means to get really highly relevant results out of Elasticsearch with whatever approach you might want to take. Vector search is often one of them, hybrid search is another. Things like ELSA, I think, are really showing the possibilities of what we're capable of here. With that, we'll switch back to the slides and just talk briefly about what we're seeing from a couple of customers. You can imagine the use cases of these kinds of queries, and certainly as I speak to customers, it's all across the board, from HR, like the example we just gave, to customer success and e-commerce search examples. And what you might notice about all the queries on the screen right here is that they all, in order to answer them, they all will require proprietary information inside the business, right? We're going to have to bridge that gap between what the LLM was trained on and the actual specific information inside of your company. And so that's really what we're aiming at here. A few things that a couple of our customers have been doing. So Cisco, and Sujith is here, and he's going to be actually speaking later today, and he'll take you through this in a lot more detail. But Cisco's been working on internal enterprise search experiences for quite some time, and they've been along this entire journey. Every time there's been a new advancement in any of these technologies, they're one of the first people we hear about doing some interesting things with it. So we've been really excited to see what they've done with their enterprise search system internally for their employees, and the kind of the rate of adoption of they've had for the technologies we brought to Elasticsearch. Similarly, another company called Relativity that does e-discovery search, and they're really looking to use kind of a RAG type system to retrieve all of the information in an e-discovery kind of case study, but also pass that to LLMs for doing things like summarization and analysis of those documents. But again, they all kind of fall back down to ultimately a RAG type implementation. So with that, I'm going to hand it back to Shay to talk to you about what's next.
So I think one of the things that I want to pause for a second and talk about what Matt showed. When we think about Gen AI, we immediately jump to think about, like, we need to use large language model, ChatGPT, or other services. But there has been an amazing progress just in this concept of transformer models. And you don't necessarily have to go and figure out how to use ChatGPT, how expensive it is, or other systems, and how do you constrain it. There's like a lot of amazing models that make a step function difference in the capabilities of search, like ELSA, that you can have access today and use as if you were using regular search, BM25 search in Elasticsearch. That includes some models that we develop internally. ELSA is an example. Or models that are developed by Microsoft, like the E5 model is a model that is publicly available, developed by Microsoft, and it's extremely capable, especially for multilingual search, for example. So you don't have to wait as a company to go and make a material difference in the experience that your users have in that search box, if that makes sense. and that makes the search box extremely more valuable. And you saw the example about Wikipedia, and I completely agree, Robin Williams is the funniest actor ever. So I approve of ELSER relevancy model. Next. So I wanted to show you a bit about where we're heading. Obviously, there's tons of work going on in Elasticsearch and in other places, but maybe a few points that help communicate the spirit of the direction that we're heading. The first one, we're going to make Lucene the best vector database in the world. We have been making significant investment to make Lucene a great vector database, and we're making even more investments as we speak as a company, Elasticsearch, together with the Lucene community, to make Lucene a great vector database. The same way that we made it a great numeric search database, geospatial database, column restore, we're making Lucene the best vector database out there. Lucene is more than 20 years old. It's one of my favorite, or I think one of the most romantic open source projects in the world. Hopefully Elasticsearch will live up to it at one point. It rhymes around a lot with things like with other open source projects like Postgres, and it survives the test of time. It was released in 1998, and it has evolved, and it's an honor to be part of that evolution, and we're going to make the investments to make it a great vector database. We'll get a chance to hear about all of the things that are happening, from SIM instructions improvements to a better product quantization and other stuff, but the end result is it is a great vector database today, and it's going to be the best vector database in the future. Next, we're going to make Elasticsearch the best at semantic search and retrieval augmented generation. Now, you've already seen that it's pretty damn good already. We've been building a lot of the components and investing in it for years now. But to be honest, I think we can do a better job in connecting all of them together. As we've been building it, there wasn't like this general theme around Gen AI, and the workflow wasn't obvious. And as a result of it, the components go deep, but they don't combine and they don't work well together. And I'll give you an example. We had a whole offsite about it, trying to figure out how to simplify things. And I want to walk you through some examples. So before, or today, to be honest, this is what it takes to try to use ELSER. And I'm going to walk you through the APIs and how it's being used. So the first thing is to go and install ELSER. Now, because ELSER is a built-in model, we know how to go and fetch it and download it and install it into our machine learning nodes, and that's not a problem. Next, we need to go and start ELSER, which is fine. You know, you install it, it's installed, but you can start and pause it, so it doesn't take resources, so you can decide when to use which. Afterwards, you need to go and define mapping. So this is your schema. You define your schema of your data. Now, it already starts to sound fishy because there's a type there called rank features. And rank features is a previous capability that we built, the ability to do sparse vectors. Now, rank features make sense in the context of just rank features. But it doesn't make a lot of sense in the context of Gen AI and vectors. It's not called sparse vectors, but we've used rank features as a way to implement sparse vectors. Next, we need to put an ingest pipeline. So the process of using a model is at ingestion. You take the data and you generate embeddings. Those are the vectors that ends up being stored, sparse or dense. And then after that query time, you need to do it. So we're going to do it at ingest time. Elasticsearch has a concept of an ingest pipeline. So when you index data, it does additional work. Obviously, here, you need to define the model ID. So I need to remember what was the name of the model that I used. And I need to go and which field is it going to use, and then some magical configuration over there. It all makes sense on its own when you build it in isolation and in a very generic way. Next, I'm going to index data, and I need to remember when I index the data to tell it to use that ingest pipeline that I just configured, because I don't want it to be indexed without that information, without generating the embeddings. And then I can go and do a search, but then when I do a search, I need to use text expansion and define the ML tokens field that was generated as a result of those embeddings. And I need to, again, remember the model ID that I'm using and go and use it. And then if I want to go and use something like RRF, then I need to go and use a query, and that's the term that I'm using, and then combine it with another query and define something called rank now at my sub-searches capabilities. Now, I think you can see that a lot of the things that we've developed go deep. Rank features is great. Its ability to store sparse vectors, ingest pipelines make sense, but they don't combine well together. You know, now that we know the workflow, the thing is that we didn't know what the workflow was. Now that we know the workflow, this is more complicated than it should be. So here's where we're heading. You define the mapping, and you just say which model you want to use. Now, because ELSER is built in, then we'll go and just use those mappings. We call this model as an analyzer. If you've been using Elasticsearch, the same way that you say this is English or this is something else, you're just going to say this is just using a model now. A model is like an analyzer, and it's using a type called semantic text, which is super simple. Like, it doesn't matter, dense vector, sparse vector, whatever, that model knows what needs to be done. I index the data. Now, because that's part of my schema, Elasticsearch will do the right thing. It will go and understand that it needs a model. It will go and generate the embeddings, index them. You don't have to configure ingest pipelines and all of the other work. Obviously, we're going to reuse all the components that we've built, but it needs to be packaged much more simply. And then when you do a search, it's a simple match query. We already know that this field is semantic search, text. We know that it's simple. We know what needs to be done. We can replace behind the scenes a sparse vector type search like text expansion and just make it work. This looks almost exactly like Elasticsearch from 10 years ago, which is pretty impressive. Like, this is amazing because it does so much more than what it used to be 10 years ago, but it's as simple as it was 10 or 11 years ago when it just gotten started. And then if you want to go and use something like RF, we're going to introduce, by the way, all of this is still in design phases, so I hope our engineering team is not going to kill me if we're going to change some of the names. I like the retriever model, by the way. My suggestion is to replace query with golden, and then I can say that we have a golden retriever query. But this whole retrieval model is, again, a new framework that is happening now in the context of the search world, where you need more than just executing queries. You need to have a kind of like a retriever search pipeline, if that makes sense, where you combine multiple search requests and being able to do linear scoring, for example, of multiple requests, like a BM25 one together with sparse text or something along those lines. So this is all something that we're in the midst of designing and developing as we speak. But you see how simple now it is to use ELSER, right? It's exactly like you used to use Analyzer in Elasticsearch, and you don't have to worry about anything. It's like super, super simple. Now, a lot of the work has already been done. There's still a lot of work left, obviously, but it's about combining these things together, and we can do it because now we understand the flow. We understand how it's being used in a practical sense, if that makes sense. Here's another example. So this uses sparse vector. What happens when you use dense vector? So this is an example with E5. So where Matt showed E5, ELSER is a sparse vector implementation, so that uses the existing inverted index semantics. E5 is a dense vector, so that uses vector search. So first of all, you go and we have a tool that can go to Hugging Face, for example, reach out to Hugging Face, take E5, download it, and install it into Elasticsearch. So that's what you do here. Afterwards, you need to go and create a field that is type dense vector, and you need to go and define the dimensions of that dense vector and what similarity it's going to use and which text field. So that's the mapping. And afterwards, you need to go and define an ingest pipeline, if you remember, to be able to generate the embeddings at the ingestion time using that model. And you need to go, obviously, and then ingest the data and define the ingest pipeline. And the search now uses KNN query, right? KNN search, because you're using dense vectors. But again, you need to define the K and the query vector builder, and then you need to remember what the name of the model was, because it needs to go and generate the embeddings at query time as well as it does at ingest time. And obviously, here's how an RF implementation look like. There's a query, there's KNN, but KNN is not really a query. It's at the same level. Again, like, it's a bit confusing in terms of why is it not a query? Is it something else? Is it a retriever? So all of this is great. Like, KNN query implementation is awesome. Our ability to go and run an E5 model within Elasticsearch, that's amazing. The ability to combine things together and generate embeddings, great. All of them work really well. They don't mesh in a great way. So here's where we're heading. Again, everything is in the schema. You just go and define actually the same type, semantic text. And now it uses the E5 model. And the model has inside it all the information that it needs, the dimensions, all of that, so we can go and understand from the model exactly what is needed. That's in the schema. That's tied to that field now. We index the data. We don't have to define ingest pipelines or something on those lines. It just index the data and immediately knows, thanks to the mapping, the definition of it. And then we go and do a match query. And guess what? We know that we can go and replace it with a KNN query behind the scene, because that's exactly what needs to be done when you query a dense vector type search. And again, using the same retrieval model, we can now make sense of the fact that there's one that is query and another one that, for example, is KNN, and make it work. So that's where we're heading. And I hope that you see in the spirit of it, like the things that has been extremely impressive, I think, what our team has done. We really invested heavily in building like great vector search capabilities in Apache Lucene, combining them together, exposing all of these capabilities that you've seen in the demos in Elasticsearch. But now we have an opportunity to significantly simplify that experience and make it as simple as Elasticsearch was for regular search, if you will, more than 10 years ago. So we want to make Lucene the best vector database out there. We're going to make Elasticsearch the most comprehensive and simple search platform in the world. What's the third part that we're focusing on? Open. We've always been an open company. And Elasticsearch needs to be extremely open when it comes to the ecosystem of Gen AI tools around it. We're going to work with every single LLM out there, public or private. That's not a problem, because we're building the pluggability to be able to do it. You're not going to be tied to a specific implementation or something on those lines. We're going to be able to host LLM models and LM models, not that large models, if that makes sense, like ELSER and E5 and others. We're going to host all of these models as well to be able to allow you to have access to all of it in a very simple and easy-to-use system. And we're going to work with all of the various workflow systems and open source projects like LangChain, and you're going to hear some of them today, and Hugging Face and Llama and OpenAI. We're going to be a system that is open to everything else that happens. We will take your private, real-time, privacy-oriented data, store it in Elasticsearch, and be able to expose it to any other system when it comes to the Gen AI ecosystem. And we're going to be able to also run some things ourselves. And you can progressively decide how much you want to rely on external tools versus use Elasticsearch. But the core of what we do is to be the best search engine in the world. We have done it for many years, and we think it's critical in Gen AI workloads. And this is exactly what we're focusing on building it today. Next, and I've talked a lot about Elasticsearch and all the work that we're doing in that stack and openness around it. I'd like to invite Ken to also talk about what does it really mean to have ELSER and Elasticsearch when it comes to our solutions in security and observability. Ken?
Thank you, Shay. And good morning. Great to be here. So as we've talked about a lot this morning, Elastic has been investing in AI and ML for a number of years, many, many years. And we've been doing this along two dimensions. A lot of what we talked about today are the things that we've been doing on the first timeline, things that we do to enable developers to build search applications and generative AI applications with these technologies, these foundational building blocks, like vector search, like ELSER, and like Esri that we recently launched. But we've also been investing on a second timeline, and that is incorporating these technologies into our own solutions. Elastic has two out-of-the-box solutions for observability and for security, end-to-end solutions for observability and security, and we've been embedding these technologies there so that you can use things like anomaly detection for observability. You can use things like ML-powered detection rules in security. And today I'm going to talk about a new thing that we've been doing called the Elastic AI Assistant. I suppose like a lot of companies these days, we launched an AI assistant earlier this summer. Everyone's been doing co-pilots and AI assistants. But I think the world of security and observability are kind of unique. They're uniquely sort of primed for disruption and to benefit from the power of generative AI. You have lots of specialized knowledge in these spaces. You have practitioners who rely on a lot of domain-specific knowledge. They're getting increasingly more difficult to hire. You have people that rely on pattern matching and processes that are fundamentally more sound and more efficiently solved by machines than humans. So I think you're going to see a lot of disruption happening in the world of observability and security because the tasks that people perform there are better handled by machines than humans. 3 of these such tasks are detection, diagnosis, and remediation. We're already seeing this with detection. So the whole promise of AI Ops, for example, was about detection, automating detection, helping you use anomaly detection, for example, to automatically detect issues in your software. You're seeing this also in security with machine language-powered detection rules. But you're also going to see this in the area of diagnosis and remediation. Diagnosis, like a lot of what we do today is we provide security analysts tools for threat hunting. But that act of threat hunting can be automated as well. And same thing in the area of observability. A lot of the diagnosis that SRE professionals do is about looking at the different signal types, using tools to correlate issues across the different signal types to get to root cause. To get to root cause, that can be automated too. And eventually, once you automate that, you can start getting towards remediation and automating remediation. I used to think that this world was far away. I don't think it's actually that far away. And I think we're actually starting to see it today in some of the tools that we're providing at Elastic. We launched earlier this summer something called the AI Assistant for Security. And the AI Assistant for Security does some simple things like it provides query conversion to help you do queries in different languages, but it starts to help with remediation as well. So it looks at a critical security issue, and it helps you figure out how to interpret that, but then it suggests sort of a playbook or runbook for how to remediate that. There's a talk later today by James and a couple of folks on my team. They're going to dive deeper into this. I encourage you to go check it out and learn more about the AI Assistant for Security. The other assistant we launched is the AI Assistant for Observability. And rather than talk about it, I'm actually just going to show it to you. This is something that we launched just a couple weeks ago. And it is in tech preview, so I encourage you to give us feedback. We're still working on it and perfecting it so we can get it to GA. But I think it's really exciting. Now, I'll walk you through a scenario here. So I'm an SRE professional, and I've gotten an alert. An alert has fired and has told me that there's a log threshold that has been breached. And you can see the alert here. There's been a spike in errors related to this set of logs. One of the things that we do right now is we automatically run a log spike analysis, so that when you open up this ticket, you open up this alert, we decorate that with some additional information so that you can get more details about why this is an alert. So we run a log spike analysis. This is essentially a machine learning process that looks at this deviation, compares it to a baseline, and determines some things that you should look at. So it's done some pattern matching, looks at the different field names and field values, and it prioritizes this. This is cool. It gives you lots of information, prioritizes what you need to look at, but this is kind of traditional machine learning. This is not special. This is stuff we've been doing for years. But what is new here is I have this new box down here called Possible Causes and Remediations. This is powered by the AI Assistant. And what I can do now is I can ask it to analyze what I've done up above and tell me what it thinks the possible root cause is and how to remediate it. And what it does is it passes all that context to an LLM. So the entire log spike analysis gets passed to an LLM, and then it determines what the possible root cause is. And in this case, this is powered by GPT-4. It's telling me that it believes the issue is related to something called PG bench, and then it gives me some steps for how to remediate this. And if you look at the initial log spike analysis, you can see, yeah, in fact, there were a bunch of issues that were high on this list that related to PG bench. So it makes sense that this would be what the LLM determines as the root cause. That's cool, but I can take this one step further. I can then start a chat with continue this chat and ask, for example, what is pgbench? And it passes the context to the LLM, and then it comes back and tells me pgbench is a benchmarking tool for Postgres. Okay, that's cool, but that's fairly simple. I can do that in ChatGPT. There's nothing special about that. Maybe it's nice that I have this in the context of my application, but there's nothing really new here. Let's get to something new. Let's get to something that really is special. What if I wanted to then ask, did this incident have an impact on my revenue on June 7th, 2022? Now, how on earth could ChatGPT or GPT-4 know that? It doesn't know the operational history of what I have. It doesn't know how to interpret this question. It doesn't know how to assess revenue impact. Well, what we're going to do now is we're going to see Esri in action. So this is the retrieval augmented generation workflow. We're going to prompt ChatGPT or GPT-4 with some additional information, including how to ask us information, how to get more information out of Elasticsearch and the AI assistant. And what's going to happen is they're going to determine that they need to get a list of service names. So they're going to invoke the function get APM services list, and we're going to then pass a list of service names, and then GPT-4 is going to determine that it probably needs to get some information from a particular service name called checkout service, and it's going to ask for APM timeline series data that is then going to get interpreted and passed back, and it's going to generate two charts, one for checkout service throughput and one for checkout service failure rate. And what you can see is, in fact, yeah, there was an impact, depression in throughput on the checkout service, and as well as a spike in the failure rates. And it's going to assess what happened. It's going to determine that, yes, on June 7th, there was an impact to the checkout service, which it believes was related, that did have an impact on revenue. And all this happened as sort of a back and forth between our assistant, powered by Esri, and the LLM. Now let's go further one more time. What if we asked it to, can you visualize my revenue data for June 7th, 2022? Again, there's a lot of additional things it needs to do. It needs to understand how to interpret revenue. What is revenue? And how do I assess that? And again, it's going to go back and forth, and it's going to ask some additional questions, and it's going to determine that it needs to invoke a function called recall, which is going to then ask the ELSER model, that has been trained on our knowledge base, how to get revenue information from us. And then it's going to determine that it needs to invoke the function lens, and then it's going to determine that it needs to plot a chart in lens that shows revenue, and it's going to finalize. It's finally going to give us a blurb that says, yes, you can visualize your revenue data. It did have an impact, as you can see here, and this is a chart that has been produced in lens that you can then drop into any dashboard. So all of this is demonstrating ELSER and Esri in action as used in the Elastic Assistant to go back and forth with the LLM to provide additional information. So I'm excited about this. You can learn more about each of these demos later today. We're going to talk a little bit more about the Assistant for Security and the Assistant for Observability in sessions later today. So thank you.
If you leave today, just remember, don't run benchmarks on production. That's always a good rule. Your SREs will thank you. But I want to touch on Ken's point, I think, here. Like many years ago, we built a search engine. And then we didn't really realize what were like logs and threats and things along those lines. But suddenly we saw Elasticsearch being used to store logs and explore them in this like SRE market and DevOps and observability. Then we started to see security people using Elasticsearch to do threat hunting. And that was pretty amazing. And we asked ourselves why. And a big part of it was because search is amazing as a technology, as an experience when it comes to exploring logs, to exploring observability data points. It's really liberating. People are like confined with their older tools around how it's being used. It wasn't open source, it wasn't open. Same thing in security. You know, threat hunting was taking ages with previous SIEM tools, and suddenly, like, you could use Elasticsearch and search your security threats very quickly and get answers, and suddenly you wouldn't, like, chasing the bad guys for years or for days until you could figure out what happened with Log4Shell or something along those lines. And then we went on a journey as a company to have complete observability and security solutions. And you can see, like, those experiences are pretty amazing compared to 10 years ago when you just had a search box where you could find, like, a list of threats or a list of logs or something along those lines. And what happens now with Gen AI, it feels like we're going a big back to the beginning. Because suddenly the importance of search becomes even more critical in these solutions. And a company that does search extremely well will be able to build the best AI assistant for observability and for security. And I think that that's a very, very exciting future for us when it comes to our solutions, for our ability to go and give you the best observability tool that you deserve, or the best security tool that you deserve. So what is the future of search for us? I mean, it's all about search. We will build curated experiences in security and observability and make tons of investments. But search is a critical component for Gen AI workflows. Sometimes all you need is search. And Elasticsearch, we are a leader in search. We've built the most popular search engine in the world today in Elasticsearch. It's very humbling. And we're going to work very hard to make sure that this remains the same. We're using the most popular information retrieval or search library in the world today, in Apache Lucene. We're going to make that Apache Lucene is going to be the best vector database out there. And we're making these investments. And we're going to make sure that it's easy and simple to use the way that it was 10 years ago. Those things are very, very complicated with models and vectors and embeddings and things on those lines. But I hope that you see that we can simplify that experience the same way that we did 11 or 12 years ago when we first released Elasticsearch. So thank you very much. And I'd love to invite Jeff from Hugging Face, a great partner of ours, to give a talk.